Okay, welcome back. This is 6.3. Now we actually want to give you some methods for solving these differential equations. Then we'll head back to some more applications, and then I think we'll have one last method towards the end there. So this is separation of variables, which is kind of what I was showing you before. We'll take a look at it in more detail though. My pen's running out of ink. So separation of variables, I'll get a different pen. Okay, so there's forms of differential equations, and we'll have a separable form. Sometimes you have to play around with it to really see if it's separable, so this is not the end-all be-all explanation. So n of x plus n of y times dy all over dx equals 0 is usually the standard form, but in order to find your solution, what you're going to want to do is get all the x stuff on one side, all the y stuff on the other. So you'll want to separate. Before you separate, usually you want to look for trivial solutions as well. So I'll tell you a little bit about that. And that's just if you have a y function on this side and you can find it equal to 0, it'll be a solution. Okay, so anyways, separating, you want to get ny dy over dx equal to negative m of x, and then, it's not technically what we're doing is taking the derivative on both sides with respect to x. Okay, so it'll look a bit like this. And then over here, these guys kind of cancel out, and you got the integral of n of y with respect to y equals negative integral of m of x dx. And then you'll have your solutions here. You try to find an explicit solution. And then on top of that, if you can find, if you put it into a form where you have a y on this side, so if you have a form of something like y prime equals m of x times z of y, and z of some particular y sub 0 equals 0, that's going to end up being your trivial solution. Y sub 0 is a trivial solution. Y equaling y of 0 is a trivial solution. Okay, so I know I ran out of room there. So anyways, it's going to be more clear when we get in there. This is abstract ideas. So you try to find an explicit solution. If you have the form, so different than this is just, I still don't use the same variable there for my x expression, but I mean, if you could get your derivative y prime equals something like this, and then you find that this z of y sub 0 is 0, y equals y sub 0 is a trivial solution to that differential equation. Okay, but hopefully that'll be more clear here as we go through. So let's go through. Number 3, we have x squared plus 5y equals dy all over dx. Okay? Right, so I'm going to try to get the y's on one side, the x's on the other. Whoops, this is equal to 0. So I copied that wrong. I was going to say that's going to be a little harder. 5y times dy all over dx equals 0. Okay, so I'm going to try to solve this thing. I'm going to get the x squared over, and I'll have 5y dy all over dx is negative x squared. I like to put my constants on the right side. You don't have to do that, but I like to. I like to put all constants on the right-hand side. Okay, so I'm going to move this 5 over to here. I'm also going to move the dx over to there. So technically, you'll end up taking the integral on both sides with respect to x, but the way they kind of educate you to do this is just to write the, and I want to move this over, sorry, I want to write dx on this side. For some reason people like that better than having them write it out the other way. Okay. And this will be all over 5. Now I'm going to integrate both sides. Over here I got y squared over 2, and on the other side I'll have negative x cubed all over 15 plus some constant. Now technically there is a constant over here, but what's happening is I'm adding it over to here and it's getting combined into this thing. Okay, so it's some constant, which is the sum of the constant from this thing and the constant from this thing. But we don't need to record that because as soon as you know x and y, you automatically know what this constant is. Okay? Another thing is you try to get into a form that is familiar. And for most of us, we're not as familiar with square root functions as maybe things that look like circles. The book will try to get rid of the fractions, so maybe multiply through by 30. I'll end up with 15y squared. I'm going to move this guy over. It'll be 2x cubed, and then that'll be equal to c. Okay, so when I write it in this form, it's kind of like the equation of a circle, which turns out to be a little bit more palatable than, you know, multiplying through by 2 and then taking square roots, and it's just a nightmare. Okay. So explicit solutions are great, but it's not in general something that's all that easy to get at. Okay, let's keep going. Number 5. dr with respect to ds is equal to 0.75 r. Okay, so this is basically an exponential growth, right? The rate of change of the population is proportional to the population at some given time. So this is a rate of change, and we should be able to handle this. All right, so there is a trivial solution here. Okay, if your y formula can be made such that it equals 0 for some particular y value, then that's a trivial solution. In this case, y is r. Okay, so note here, r equaling 0 is a solution. Okay, let's go ahead and separate. So I'll move the r over here. Integrate. Exponentiate. Whoops, I forgot my plus c. And then finally drop the absolute values, replace this thing with a constant. It'll be plus or minus e to the c. Let's just replace it with a constant. Because as soon as you know r and s, you're going to know what that constant is. Okay, there's no reason to make it more complicated than that. Okay? And then that would be your solution, your general solution. So you're going to also want particular solutions, and to get the particular solutions, we'll need some sort of initial condition. Okay, so part B, I guess, finding particular solutions. Let's take a look. So number 16, I have the square root of x plus the square root of y times y prime equals 0, and y of 1 equals 9. Okay, so separate. Let's write y to the 1/2 instead of root y. That would be dy over dx equals negative x to the 1/2. Okay, separate, get that dx to the other side, and then integrate. Okay, and if you want to clean it up a bit, that's fine. So I'll move this over, multiply by 3/2. It'd probably been better to put the x first. Okay. But there's my particular solution. Now I want my general solution, and you have to use the initial value. And that will tell you what c is. Okay. Okay, so let's try that. Y of 1 is 9, so y is 9 to the 3 halves plus 1 to the 3 halves. 1 to any power is 1, so let's just put that. 9 to the 3 halves, that's 9 to the 1 half cubed. 9 to the 1 half is 3. 3 cubed is 27. So C must be 28. So finally, our particular solution is x to the 3 halves plus y to the 3 halves equals 28. Let's try one more, and then we'll do some orthogonal trajectories. Okay. So again, we're looking for a particular solution. So let's separate. Okay. I'm going to move this over, move that over there. I don't think it's clear if there's any, there is a trivial solution there. I think 1 is a trivial solution. Yeah, but we're not interested in that. Let's keep going. So I'll have y times dy over dx all over the square root of 1 minus y squared. On the other side, I have x over square root of 1 minus x squared. Okay, so y over that dy equals x over square root of dx. Integrate both sides. You need a u sub for the 1 minus y squared. On both sides, basically, it'll be the same kind of integral. So on this side, I'll have ultimately negative 1 half times 1 over u to the 1 half, which should just be u to the negative 1 half du. Let's use a different variable on this side. Negative 1 half z to the negative 1 half dz. You can multiply both sides by negative 2. That'll get rid of that issue. But then when you integrate, you'll have u to the 1 half times 2 equaling z to the 1 half times 2 plus some constant. I'm going to multiply everything by 1 half and then back substitute. So I'll have the square root of 1 minus y squared equals the square root of 1 minus x squared plus c. And I think I'll just leave it like that. Let's go ahead now and find the particular solution. Y of 0 is 1. So y is 1. I got 1 minus 1 squared is 1 equals the square root of 1 minus 0 plus c. So it looks like c is going to be negative 1. Right? So this would be 0. This is 1. Move it over. C is negative 1. So our particular solution, 1 minus y squared minus the square root of 1 minus x squared is negative 1. Okay, one last problem then, it's the orthogonal trajectories. So sometimes we're very interested in figuring out where something is orthogonal. And you think about it, it has to do with flow through objects, right? So if I want to kind of find out how much is going through the membrane of my heart, you're going to want to think about blood perpendicular, moving perpendicular to the surface of the heart. How much is going to go through the heart membrane? So finding where things are orthogonal, in other words, perpendicular, becomes very important later on in that kind of work, at least. And it's pretty easy to do. Trajectories. What you're doing is, you're given a differential equation, or you're given a family of curves. Okay, and you want to find another family of curves that are all orthogonal or perpendicular to this. For example, if you have a family of circles, the family of curves that are perpendicular to the circles will just be straight lines, a bunch of straight lines going through there. So at any point, like right here, the line and the circle are perpendicular. Okay, so that's the game you're playing. So how do I do that? Well, you're going to first solve for C. So you get C equals y over e to the x. Then you can differentiate implicitly. So this will be 0, the derivative of a constant is 0, equals, and I think I'm going to rewrite this and exploit the product rule. So the derivative of y is y prime times e to the negative x, and then plus, leave y alone, and then the derivative of e to the negative x is negative e to the negative x. Okay. Then I'm going to solve for y prime. That gives me the differential equation for this family of curves. Okay, so I'll have y prime e to the negative x equals y e to the negative x. Divide both sides by e to the negative x and get y prime equals y. Okay. So that goes with this. To get the differential equation for the orthogonal family, you just take this thing and take its negative reciprocal, which may sound familiar to you. That's the slope of a tangent line, sorry, the slope of a line that's perpendicular to a line with given slope m, -1 over m, the negative reciprocal, right? So this new family will be -1 all over y, and then we solve this differential equation. Okay, so I'm going to multiply both sides by y. I get y times dy equals negative dx, and then integrate both sides. And then I'm going to multiply through to get a nicer looking. And that would be a solution which you could plot and check. Okay, so it'd be a bunch of, I guess, sideways facing parabolas that will be perpendicular to that family. So this family and this family, if you graphed it out, you get some sort of situation where all the curves are perpendicular at any point. Okay, thanks, bye.